For the last video introducing this course, I want to talk about where environmental science comes from. There can be a big difference between the way that many people have experienced science in high school or even in college and the way it's actually done. Sure, there are many examples of carefully planned experiments, replication of prior studies, and very monotonous experiments that take hours in a lab. But for all of those types of studies, there are also many other approaches to science, and often many examples of creativity, or hunches, or just plain outright luck that go into scientific research. So I want to do three things today with this video. First, I want to tell you a story about a particular piece of research that I was involved with. Second, I want to give you a sense of what goes into creating peer-reviewed research and why this is so important. And lastly, we'll talk a little bit about synthesis reports, which are becoming increasingly important in the field of environment and environmental science and policy. Here you go, a research paper. It looks pretty exciting, doesn't it? Well, to make this a little bit more interesting, I'm going to tell you the story of how this particular research paper came to be. And then we'll use this to explore the overall process about how environmental science is done and then actually published in the end. The title of this paper is Increased Dust Deposition in New Zealand Related to 20th Century Australian Land Use. And this is work that was done by a former PhD student in my research group, Janice Brainy, who now teaches at Utah State University. So this work, like all scientific research, goes through a lot of different steps. In a big picture sense, we have the first stages of research and then publication, like this paper here. But if science stopped at that point, we would have a giant mountain of papers, but no clear understanding of how the world works. And building that broader understanding of environmental science requires evaluation and synthesis. And that happens across many different papers with many different people. And through it, we build a coherent, consistent, and clear explanation of environmental change. So let me tell you a little bit about where it starts. I'm going to summarize this whole study in one slide. So here it goes. Atmospheric dust is made up of mineral aerosols, otherwise known as dirt or soil, that are blown long distances, often after lands are disturbed, maybe by farming, maybe by something else. This dust in the atmosphere is actually very important to climate change, and the loss of soil has negative consequences for the ecosystems that are being eroded, and it can impact the places where it falls. In this study, we went into the New Zealand Southern Alps and used lake sediments to reconstruct a multi-hundred-year record of dust deposition. And what that shows, in a very simplified way, is that dust deposition in New Zealand rose dramatically at the same time that the Australian landscape was modified through mostly sheep grazing. This may not sound too exciting, but in fact it's something that has happened in many places, including the United States. And these changes have long-term consequences for desert ecosystems and for high-altitude environments. So let's now talk about how we actually did this study. Step one in research is usually to get money, because things like helicopters are pretty expensive. For this work, we got a little bit of money from a National Geographic Explorers grant with a proposal to look for signs of Australian land use in the high elevation portions of the New Zealand Southern Alps. To do this, we flew into remote lakes in helicopters with a ton of supplies, including rafts, and we then proceeded to extract lake cores from these settings so that we could look for the accumulation of dust. To get our lake sediments, we went out on boats with coring rigs. We pulled sediments up from the bottom of the lake to the surface, and then we brought these back and painstakingly separated individual layers of sediment out into plastic bags. We brought those back to the United States for a range of geochemical and isotopic analyses that would allow us to separate dust from the surrounding bedrock. This clearly is a fun part of the research, but it is really the first step. The path to publication is a long one, and it looks like this. First you do the work, then you analyze the data, summarize the results, and you start writing a paper, often getting feedback from collaborators and colleagues along the way. And then finally, usually months, if not sometimes years from the start of your work, you submit the paper to a journal. There are many types of scientific journals covering many different fields, and in most cases, the editors of journals are also scientists with a great deal of experience in the field. So once you submit the paper, the editor evaluates it and decides if it's appropriate for the journal. And if he or she thinks it is, they send it out for anonymous review, usually from 2 or 3 scientists who also work in the field. After another few weeks, the comments come back from the reviewers. And this is usually the part that most scientists dread, because these reviewers may tell you that you did something wrong, or you described the study poorly, or that you're completely out to lunch and you just did not do your homework before submitting the paper. Hopefully, if you're lucky, they still think that there's value in your work and now you get a chance to revise your paper. So you send it back out to your collaborators for comment, you write up a response to the reviewers, and you send it back to the journal. The editor then reads that response, may choose to send the paper back out to the same reviewers or maybe even somebody different. And finally, hopefully, at the end of all of this, the paper gets accepted and published. It's a lot of work, involving a lot of people and a lot of brain power. And that is why peer review is so important. The process of peer review is one of the key things that sets scientific research apart from other things we do in society. Through this process, the idea is to catch mistakes, correct misinterpretation, and improve research so that by the end of all of this work, we actually learn something from the study. Now, sometimes peer review fails. Papers get through and there are mistakes. Maybe a reviewer didn't read it closely enough, or an editor just wasn't being careful enough. Maybe somebody falsified data. But if the system works, these mistakes get caught and the papers are corrected, often publicly in the same journal where they were published. So for everyone thinking about environmental science, this process of peer review is what tells you that the information you're looking at is of high quality and has been thoughtfully evaluated by people who know what they're doing. And if it has been through that process, you can then have much more confidence that the information, the data, and the conclusions that you're reading are correct. Once a paper is published, it becomes part of what's called the scientific literature. Within the environmental sciences, and also within other fields like the medical sciences, there is often another step that becomes very important, and that is synthesis. This takes many different forms, but one you may have heard about in the environmental context is the Intergovernmental Panel on Climate Change, the IPCC. The IPCC is made up of hundreds of scientists from countries around the world that work for several years to summarize the state of research around climate. It, like other synthesis activities in environmental research, often takes place under the auspices of an international organization, in this case, the United Nations. The IPCC process has rigorous standards of what information to include or exclude. There's an extensive peer review process, and when complete, the reports must be approved by the countries that are involved. These types of processes have become very important because they give a rigorous, careful, state-of-the-art analysis of where a field is at. This then can become the foundation for a strong policy or for other interventions that address an environmental problem. To wrap up this video, it's important to understand that science is a process. It isn't a simple start and stop activity where you didn't know something at the beginning and now you do at the end. Science builds on others' science, and that's only possible because of peer review. That's why you often hear people say that peer review is the gold standard for research. More and more, we have this additional step of synthesis so that we can use scientific information more effectively to address problems. 2 last points. First is that information is going to change as we learn more. Sometimes people think that change means we're uncertain, but in fact, change is part of science. And when old advice becomes new advice, or old understanding, new understanding, it means that our science is getting stronger. So my advice to you is to be critical of what you read, but I would also say that at some point you have to trust the experts. You probably don't want to get your medical advice from an auto mechanic, and you probably don't want your car fixed by an MD. Scientific fields are highly specialized, and to become an expert takes years. So lean on that judgment when you can. And just in case you're watching closely, that is in fact a Russian tank with a set of scientific instruments attached to a crane arm welded on top. Sometimes you got to be creative in science, but that's a story for a different time.